What is VSEPR theory? Well, VSEPR theory stands for valence shell electron pair repulsion theory. It takes into account that in any molecule there are regions of electron density. VSEPR theory assumes that due to electron-electron repulsion, because of the like negative charges, these regions will be arranged as far apart as possible, and these arrangements will result in unique geometries to achieve the minimum energy for a compound. Before we begin, let's look at hybridization, which is essential to understanding why these shapes are formed. To begin, we'll look at hybridization in methane. In methane, carbon has 1 2s and 3 2p orbitals available for bonding, and hydrogen has 1s level available. Experimental data shows that it is really the available orbitals around the central atom, in this case carbon, that matter. If all of these orbitals are added together, you have 1 s orbital and 3 p orbitals, so hybridization is sp3. This may seem hard to understand, but it's easier if you think of the exponents as regions of electron density. 1 plus 3 equals 4 regions of electron density as seen in methane. Now let's look at some examples to make sure that you understand it. First, we'll look at carbon dioxide. As you can see, there's 2 regions of electron density, the 2 oxygen atoms, so the hybridization is sp. Now we'll look at ammonia. There's 4 regions of electron density, the lone pair of electrons, and the 3 hydrogen atoms. Make sure that you count lone pairs, so the hybridization is sp3. Let's start with the basic shapes or geometry that these molecules can form. The most basic shape is linear. Linear geometry can be exhibited in beryllium fluoride. In this case, it's shown as beryllium chloride. Since there is equal repulsion from both unpaired electron pairs around the central beryllium ion, we can predict the shape to be linear. Our prediction was correct, and beryllium fluoride forms a linear shape. The bond angle around the central atom is 180 degrees, and the hybridization around this atom is sp, for 2 regions of electron density. The next shape is bent. Now there are 2 variations of the bent shape. It can occur with 1 unbonded electron pair, as shown in sulfur dioxide, or with 2 unbonded electron pairs around the central atom, as shown in H2O, or water. In each molecule, the shape is bent due to repulsion of the lone pair of electrons around the central atom. Now H2O is one of the most common bent molecules, and its specific bond angle is 104.5 degrees. For a bent molecule with 1 unpaired electron pair, as shown in sulfur dioxide, the bond angle is less than 120 degrees. For a bent molecule with 2 unpaired electron pairs, such as water, the bond angle is less than 109.5 degrees. Make sure to notice that a bent molecule can occur with either sp2 in sulfur dioxide or sp3 in H2O, and those are the 2 types of hybridization. The next shape is trigonoplanar. A trigonoplanar shape occurs when there are 3 atoms around the central atom in an sp2 hybridization. Repulsion between the 3 electrons arranges them in the corners of an equilateral triangle in the shape of the least energy. Trigonoplanar geometry is demonstrated in boron trifluoride. In any trigonoplanar molecule, the bond angle is exactly 120 degrees, and is only on one plane. Previously, we only looked at molecules that occupy space in 2 dimensions, but if there's an sp3 hybridized molecule with 4 atoms around the central element that expands into 3 dimensions, it creates a tetrahedral shape. Methane exhibits the tetrahedral shape and is illustrated below. All tetrahedral molecules have a bond angle of exactly 109.5 degrees. Our next shape is trigonal pyramidal. Trigonal pyramidal occurs when there are 3 atoms bonded to the central atom with a lone pair of electrons. This lone pair rebuilds the bonding electrons down into a trigonal pyramidal shape with a hybridization of sp3. This shape is exhibited in ammonia, and all trigonal pyramidal molecules have a bond angle of less than 109.5 degrees. Now we'll look at shapes with a hybridization of sp3d. The first shape will be trigonal bipyramidal. Now this shape is another 3D molecule that exhibits a hybridization of sp3d. It is unique in that it has axial and equatorial positions with different bond angles respectively. This unique shape can be seen in phosphorus pentafluoride, where the bond angles of the axial bonds are 120 degrees, while the equatorial bonds are 90 degrees. The equatorial bonds are the ones that are at a right angle to the central atom, and the axial bonds are the ones that are at 120 degrees. Our next shape is seesaw. Seesaw is a unique variation of the trigonal bipyramidal shape in which the top bonding electron pair, one of the equatorial pairs, is replaced with a lone pair of electrons. This lone pair repels the bonding electron pairs more than just a paired electron, forming a seesaw shape with bond angles that are less than 120 degrees and less than 90 degrees. Now the angles shown in the picture are additive, so divide them by 2 and you'll find the individual angles. The next shape is T-shaped. In a T-shaped molecule, there are 2 unpaired electron pairs around the central atom. These pairs repel the remaining atoms down to form the shape of a T, with bond angles less than 90 degrees, which is illustrated in chlorine trifluoride. The next shape is octahedral. In an octahedral molecule, there are 6 bonding electrons around the central atom. The most agreeable place for these regions of electron density are in the corners of an octahedron. An octahedron has 8 sides, but we are only concerned with the vertices, the 6 vertices, where the atoms lay. Octahedral molecules exhibit sp3d2 hybridization. This shape is exhibited in sulfur hexafluoride. Octahedral molecules have bond angles of exactly 90 degrees. For the first practice problem, draw a boron trifluoride, including all lone pair electrons, and label the bond angles between molecules. Boron trifluoride exhibits a trigonal pyramidal shape, with bond angles of 90 and 180 between the regions of electron density. Make sure you put the unpaired electrons around the central atom, which exceeds the Ottech rule for this example. Now, draw the molecular geometry of a seesaw-shaped molecule and explain why the molecule is shaped this way. The molecule should look like this, with 1 lone pair of electrons around the central atom. Now it's shaped this way because the lone pair repels the other atoms down, and it's similar to the trigonal bipyramidal shape. It's only different because of the lone pair of electrons. And if you wanted to include the bond angles, they're less than 90 and less than 120. In an octahedral molecule, how many regions of electron density are there, and what is the hybridization around the central atom? In an octahedral molecule, there are 6 regions of electron density, and the hybridization is sp3d2 due to these regions of electron density. For our final problem, explain the difference in shape between water molecules and carbon dioxide molecules using VSEPR theory. Water has sp3 hybridization because it has 2 lone pairs on the oxygen atom. This repels both hydrogen atoms down and results in a bent structure of 104.5 degrees. Carbon dioxide has simple sp hybridization and a linear structure because it does not have any lone pairs of electrons that will repel the oxygen atoms. These types of charts are useful in reviewing VSEPR. You can see the trends as the hybridization or bonding atoms increases. It's helpful to use these before the test to make sure you have a firm grasp of VSEPR, its shapes, and the bond angles.